Hi there, Mr. Sutton with the AB Calculus 614 homework solutions on volume with known cross-sections. For this problem, we have a base of a solid enclosed by a semicircle and the x-axis, and cross-sections with respect to the x-axis are perpendicular to the x-axis are rectangles, heights twice that of the side in the xy plane. So we'll start this by figuring out the area of the cross-sections in terms of x. Our area in general, a of x, is going to be base times height. But we need to have only one variable. Let's express this in terms of the base first, and then we'll talk about the x's. So they said the heights are twice that of the side in the xy plane. Well, they're basically saying the height is twice the base. So this is b times 2b, which is just 2b squared. All right, so what is b? Well, b is going to be the distance between your function and the x-axis. So that's going to be just the square root of 49 minus x squared, because it would be this minus 0, so it's just this. So we have 2 times the square root of all this squared. Now for the limits of integration, this semicircle and the x-axis equal each other when x is positive or negative 7, we can see here, or you could do it more algebraically. So then we have the integral for volume. We have the integral from negative to positive 7 of this area formula here. And now the rest happens on the calculator. So to make this a little bit easier on myself, I'm going to put the square root of 49 minus x squared, all of that in y1, in my y equals. And now I just have to do 2 times that squared, so 2 times y1 squared. Use alpha trace to call up y1. And now let me just do my integral. So math 9, we're going from negative 7 to 7. And alpha trace, I need y2 for this, because that's where I put the area formula. Dx comes out to 914.667. For this problem, we have the base of the solid as a region enclosed by this upside-down parabola and y equals 0. Cross-sections are isosceles right triangles with one leg in the xy plane. So let's get our area formula to start off with here. So let's just think this through. If we have an isosceles right triangle, that means 2 legs are the same. One leg is in the plane. Now the right angle in an isosceles right triangle is between the 2 legs, because the third side across from the right angle is the hypotenuse, not the leg. So that means we have one leg down here, one leg sticking straight up here. So we have basically a base and a height for our triangle with these 2 legs. So my area formula in general, 1/2 base times height. But because this is an isosceles triangle, the base and the height end up being the same exact thing. And the key here is that one of the legs is already in the xy plane, so you know the other leg has to be the height. So I'm going to write this as 1/2 base squared in this case. Now what is the base? Well, that's just going to be the distance strip between my bounding functions, which in this case is just this parabola right here. So we have 1/2 times all this craziness squared. That's our area formula. And now for the limits of integration, we need to set this stuff equal to 0. And if we do a little bit of algebra here, let me see. I'm just going to multiply everything by, let's just multiply everything by negative 4. So that would be x squared minus 16 equals 0. Add the 16 and square root it. We have x is going to be plus or minus 4. So for my volume, I have the integral from negative to positive 4 of this area formula with a little dx after it. And now it's time for some calculator action. To be successful on this one, I'm going to do a little bit of work in my y equals. So for y1, that was just this function up here, because that's kind of nasty to have to try to rewrite in the middle of an integral. And for y2, that's my actual area function. So that's just going to be 1/2 times this craziness in y1 squared. And now let me do my actual integral. So math 9, integral from negative 4 to positive 4. And now I just have to do alpha trace y2 for my area function, dx, and that's 34.133. For this problem, base of a solid is the region enclosed by this semicircle and the x-axis. Cross-sections are isosceles right triangles with one leg in the base. So here's just a 3D representation of this, just because I can. So there's my semicircle. Here's my isosceles right triangles with one leg in the base. we're going to start by getting the area of the cross-section, this triangle area, in terms of x. That's going to be a of x equals 1/2 base times height in general. But now since this is a right isosceles triangle, here's your right angle here, that means that this leg and this leg are the same distance, so the base and the height are actually the same thing. So this is then going to be 1/2 base times base, or 1/2 base squared. And what is the base? Well, it's just the distance between the semicircle and the x-axis. So that's just going to be 1/2 times the square root of 9 minus x squared, all that squared. Now I need my limits of integration. So that's where my semicircle equals 0. And even if we didn't have the graph here, we can see that if I plug in 3 or -3, that's going to zero this out. So my volume then will be the integral from -3 to +3 of this a of x I just wrote out. And now I need the calculator. So to prevent some silly mistakes here, I'm just going to do as little as possible at a time. I'm going to put my semicircle as its own y equals y1. And now I'm just going to take half of that function, or half of this function squared. So this is 1/2 base squared right here. Now going to my integral, we do math 9. We're going from, let's see here, -3 to 3. And then we're just going to do alpha trace y2, where I stored my area function, dx. And that comes out to exactly 18. Nice. On this problem, we're told the base of a solid is the region enclosed by this semicircle here and the x-axis. Cross sections are semicircles. So here's a picture of what's going on here. We have a base, the area that's a semicircle, but we also have cross sections that are semicircles. So somebody really likes semicircles, whoever made this problem. Let's start by getting the area of these semicircle cross sections. So for that, I'm going to use the general formula a of x equals 1/2 pi r squared over 2, or 1/2 pi r squared. The radius, though, you've got to be careful here. So normally, the thing that you plug in for your area formula variable is the distance between your two bounding functions. In this case, though, this formula uses a radius, not an outright base. The radius is just half the distance across this semicircle cross section here. So in this case, we're not doing square root of 16 minus x squared. We're doing all of this divided by 2 for the radius. So I'm going to write this as 1/2 pi times, and I guess I could say 1/2 radical 16 minus x squared. And that inside piece is being squared. Well, actually, everything in here is being squared. This divided by 2, that whole thing is the radius, so the 1/2 gets squared as well, and that's an important point here. All right, let me find my limits of integration. I'll set my semicircle equal to 0, and I'm going to get plus or minus 4 if I do all the algebra on this. So I need the volume then from negative to positive 4, so integral from negative to positive 4 of my a of x formula. And now let me just carefully put this in the calculator. So most of my heavy lifting on the calculator I'm doing in the y equals. For y1, that's where I'm putting my radius here, so y1 is my radius. And then I'm going to take that radius that I stored in y1, and I'm going to do 1/2 pi times the radius squared. So alpha trace y1, so that I don't have to rewrite all of this and worry about parentheses. All right, going back to the main screen, do math 9, integral from -4 to positive 4, alpha trace y2, where I stored my area function, dx, and I'm getting 33.510 out of this. On this problem, they're telling us that R is the region in the first quadrant bounded above by the graph of y equals ln of 3 minus x for 0 to 2. And then they're telling us this is the base of a solid with cross sections that are squares, perpendicular to the x-axis. So what's the volume of this thing? So just as a 3D model of this thing, if you wanted it, here's what's going on. We've got this ln function being graphed out, and we've got some squares popping out of that. All right, so let's start by getting the area of the cross section. So those are squares. We can just write a of x equals s squared, but we need to express this in terms of x so that we can actually integrate it. So the side of the square, the base of the square, which is also the height, that's just going to be the distance from the x-axis to the ln function. So I'm just going to put in ln of 3 minus x, that whole thing squared. So ln squared of 3 minus x, I guess you could write it as. And then we already have the limits of integration. They gave that to us, 0 to 2. And you can see here that we're crossing the x-axis at 2 if you were to graph this out on a normal graphing calculator. Yours, unfortunately, does not do 3D models. So we have the integral then from 0 to 2 of my a of x function I just wrote, dx. And now I have to do it on the calculator. So to make my life a little bit easier, especially on this problem with an ln involved, I'm putting my original function, ln of 3 minus x, as y1. And then for my formula for my area, I just have to square what I had there. So I'll just square it like this and not have to worry about parentheses. Now I do math 9 for my integral. That's from 0 to 2. And now I just do alpha trace y2, because that's where I stored area, dx, to get an answer of about 1.029. And that's going to match answer choice B. For this problem, the base of a solid is the region enclosed by this curve here, and they're actually showing us that in the figure. So it's kind of like an ellipse, but it's a little bit flatter at the ends. So anyway, for the solid, each cross-section perpendicular to the x-axis is a semicircle. What's the volume? Okay, so we have to start with our area formula for the cross-section, semicircles, so we can write a of x equals 1/2 pi r squared. But getting the r is a little bit trickier on this one. So the r is going to be half the distance from one end of our solid's area to the other. So we have to first get this in terms of y, because if we're talking about distance from the x-axis or just up-down distance, we need y equals. So let's rearrange this formula a little bit. I'll start by subtracting x to the 4th over 16 from both sides. And then I have to multiply everything by 81. I'm going to do that, and I'm just going to leave all this in a parentheses next to the 81. Then I need the 4th root of everything. And since I'm taking the 4th root of an equation, I need to do a plus or minus. It's an even root, so I need a plus or minus. So when the dust settles, I've got plus or minus 4th root of 81 times 1 minus x to the 4th over 16. So a whole bunch of algebra happening there. And now I'm going to use this to figure out my radius. So down here I've got a 1/2 times pi times 1/2. And now I'm just going to take half of the distance from here down to here. The top curve is given by positive all this stuff. The bottom curve is given by negative all this stuff. So I've basically got one of these radicals plus itself inside here. And once I take half of this radical plus itself, I square that, and that gives me my radius squared. So this is kind of gnarly to enter in the calculator if you're not being a little bit clever about it. So let me show you in a minute what that looks like. Before we do that, though, limits of integration on this one. Well, we can see from the picture we're going from -2 to +2. So let's go with that. So our volume then, we have the integral from -2 to +2 of, well, I really don't feel like rewriting all of this. So I'm just going to write a of x dx. Now I have to do some work on the calculator. So I'm going to do a little bit of work in my y equals, and then hopefully it'll save me a lot of work later on. First, I'm going to enter this 4th root function. So for that, I'm going to go to math, and there's a special option, math 5 here, lets you enter special roots. So this is the 4th root that I want. There we go. You could also use the 1/4 power, but this looks fancier. So we've got 81, parentheses, 1 minus, I'm going to do fancy fraction here, alpha y equals, and I'll do x to the 4th, well, that's not what I wanted, there we go, x to the 4th over 16, and close that parentheses, and now I've got that function entered, and can reuse it whenever I want. All right, now I'm going to start making my area function out of this. So I'm going to be a little bit clever before I start typing stuff in the calculator. If I take this radical and essentially add it to itself, I've got 2 of these radicals. If I then multiply that by 1/2, I've got 1 of these radicals. So when I do this, I'm really just going to do 1/2 pi times y1 squared. So alpha y equals, let me get my 1/2 here, 1/2, and then we're going to do pi, And then, again, if I add this to itself and take half of it, I've just got itself that I'm squaring here. So y1 squared. So there's my area function now. Let me go ahead and take the integral of all this. So let me escape, and I'm going to do Math 9, integral from -2 to 2. Alpha trace, y2 is where I just stored that crazy area function, dx, and press enter and hope for the best. So it's taken a while to think about this. We'll give it a moment here. It's asking, what did you just do to me? That's all right, calculator. I have faith in you. So I actually did another like 20 seconds of waiting off camera, but eventually it gave me an answer, 49.425. That's one of those don't stop believing moments. And then we've got choice E that matches that. For this no calculator problem, we're given the base of a solid is a region bounded by the x-axis and this graph, which is a semicircle. For the solid, each cross-section is a square, and this is perpendicular to the x-axis. We want the volume of the solid. So here's a 3D representation of the situation. So we have some semicircle with some squares coming out of it, and this isn't the exact semicircle that they gave us up here, but it'll do for visualizing this. So we need the area of the cross sections, and then we're just going to integrate that across the interval without a calculator. So I'll start with a of x equals s squared because we have squares for cross sections. The side of the square is just going to be the distance between the x-axis and this graph, which is just the square root of 1 minus x squared. And we're squaring all that. Now, because I'm doing this without a calculator, I am actually going to get rid of the radical by squaring it. So I have 1 minus x squared is my actual area formula that I'm going to be using. Now, before I can set up an integral with this, I need to find my limits of integration. That's going to be whatever makes this square root function equals 0 because it's intersecting the x-axis. Those are the bounding curves. So let's see here. We could do a little bit of algebra, square both sides, subtract 1, divide by -1, square root. Eventually you end up with plus or minus 1 for your limits of integration. So now we're going to take the volume by doing the integral from -1 to 1 of this area formula here, 1 minus x squared dx. And we're just going to go step by step and integrate this. So for my antiderivative, I've got x instead of 1, minus, this is going to be 1/3 x cubed. We're going from -1 to 1. So I have all of this stuff with 1 plugged in, minus all this stuff with -1 plugged in. For this first brackets here, I essentially have 1 minus 1/3, which is 2/3. Over here, I have -1, and this is actually 4 negatives altogether, so this is going to be plus 1/3. So we're doing -2/3 in here, but we're subtracting -2/3, so that's positive 2/3. Again, no calculator, so you had to be careful with this, and that adds up to 4/3, which gives us answer choice B. On this pre-response problem, calculator-based, f and g are the following functions given here, and r is this shaded region. They gave us a graph of it, and they even told us which one of these was f and which one was g. That was so nice of them. So we want to find the area of this r region. Okay, so for area, I'm going from left to right and doing top minus bottom function in an integral. So I need to figure out my limits of integration. I know they're intersecting here at 0, but what's this other spot here? So let me put these in my calculator and find the intersection. So here I am in my y equals. For f, I'm putting that in my y1. Here's my y2 representing the g function. I have no idea what the window should be on this. They didn't really give me any kind of clues other than the fact that we're to the right of the y-axis. So let me do just zoom 6, and we'll see how zoomed out we are when we do this. Okay, it looks like we're pretty zoomed out here. So there was my sine function. There's my g of x function. I'm going to do zoom 4. That'll get us a little bit closer. Still not the exact picture they're showing us, but it's a little bit better. And we intersect, it looks like, at 0 and this other spot. So let me do second trace, option 5, intersect. Let me arrow my spider over to that intersection spot. Enter, enter, enter. And that's coming out to about 1.1357. So we can say f of x equals g of x. We're telling people, hey, we're looking for the intersection. Happens at x equals 0, and at x equals, I'm going to call this k, which again is 1.1357. And on my calculator, I'm actually going to quit out of my graph, and I'm immediately going to store what I just got as my variable, my constant, my k value here. So I'm going to store this as alpha k, and now I can pull that back whenever I need it. So now I'm going to need the integral from 0 to k, and let me just write this down. Integral from 0 to k, this is going to give me the area, and I need to do top minus bottom. So f of x minus g of x dx, and then let me go back to the calculator to do that. So I'm actually going to put f of x minus g of x, which in this case is y1 minus y2, in my y3. Just in case I ever need to use that particular expression again. And then let me quit out of there. I'm going to do math 9. We're going from 0 to k, so alpha k. And then now I've stored that in y3, so I'll just do alpha trace y3. This is really y1 minus y2 dx, and hope for the best. 0.429 is what I get out of that. For this part, we want to find the volume by revolving r around the x-axis. So I have the same limits of integration, 0 to the k value I found in part A and stored in my calculator. The general setup here, since I'm going around the x-axis and there's all this space between my bounded region and my axis of revolution, I'm going to need washers on this. So I'm going to do a of x equals pi times big R minus little r, and both of those are being squared. For my big R, that's how far my outer part of my region is from the x-axis. So that's just going to be the f function, and I'm going to have to square that. For little r, that's this inner function here. That's the g function being squared now and subtracted. And let me put all this in the calculator. So this is going to be integral from 0 to k of a1 of x dx. The reason I'm calling this a sub 1 instead of just a of x is that I'm going to need to make another area formula for the next part of this problem, so I don't want to confuse it with the area formula I'm making on part B. Anyway, let's put this on the calculator. So this time around in y4, I'm putting this stuff essentially. So we have pi, we have f of x squared, we have g of x squared. Quitting out of there now, I'm just going to go back to my input from part A, where I did the integral from 0 to k of y3, and I'm just going to snag that input, and I'm going to replace y3 with alpha trace y4. Saving all sorts of time doing this. That gives me about 4.267. For this part of the problem, they're telling us that our region is the base of a solid, and this solid has cross-sections perpendicular to the x-axis that are semicircles, with diameters going from f of x to g of x, and we want the volume. All right, so we have these semicircles kind of protruding out of our bounded region here, and in order to find the volume of the solid that we form from doing that, we need to first get the area of the cross-section. So semicircle area in general, and I'm going to call this A2 of x because we already used up A1 on the last problem. So A2 of x, I'm going to say, is 1/2 pi r squared, half the area of a circle. Now for the radius, we can't just say f of g, or f of x rather, minus g of h, because as they told us here, that's the diameter. In fact, they spelled it out. Usually they don't even tell you that. But all the way across gives you the whole semicircle's base, the diameter. We just want the radius. So we need to use half of f of x minus g of x for the radius. And now once we've done that, the limits of integration, those are still going to be 0 to k like I found on the last few parts. So our volume then is going to be the integral from 0 to k of this a sub 2 of x dx that we just came up with. Calculator again. So going back to my y equals, I'm going to put this area formula in as my y5 here. I usually never get up to 5. So we have 1/2 pi times, and then we've got f of x minus g of x over 2, all of that squared. Going back to my main screen, I'm going to yank my input from the last couple problems. This time we're going with y5 in here for the area instead of y4, but we're still going from 0 to k, so everything else is completely the same. So alpha trace y5 now, and enter. And that gives us 0.078, which doesn't seem very much, but hey, that's what the calculator says, so we're going with it.